then how much ever the error is at the output layer, this guy didn't cause it. It's not connected to it. You see what I'm saying? So that's basically the backpropagation idea. Backpropagation just takes the error at the only place where we do know and apportions it to the middle layers. And once I apportion it to this layer, then if there are more layers, I can apportion it to them too. That's basically what happens. And it's just almost as ad hoc sounding as expectation maximization. And it too can be seen as doing a certain kind of gradient descent in this case, as against that guy who was doing gradient ascent. And if you remember in the EM, we talked about this likelihood function might have multiple maxima, and when you do gradient ascent, you might get stuck in one of the local maxima. The same thing is very, very likely, extremely likely, for the multi-layer neural networks too. Which is actually why, in fact, for the longest time, multi-layer neural networks, training of them was extremely time-consuming process. You will take basically, you will need a large number of training examples and multiple iterations to the training examples to actually get the weights all come, because there's so many weights and they all have to come to the right valuation so that the training error is reduced. Okay, so that's basically what happens in the multi-layer neural networks in terms of, so you can think of what happened, you can think of backpropagation is analogous to EM on the Bayes network side. Okay, and then where do you get the topology here? I told you, basically it's an engineering issue. You try to start with some sparse topology and try to start with a sparse topology and try to keep adding extra links, extra edges. And of course, as you keep adding extra edges, likelihood can only improve. Data likelihood can only improve. But you also have a penalty term, which is proportional to the complexity of the network, which is the number of edges that are in the network. Okay, and so presumably you will get, if you do this in a full optimization, then you will find a particular topology that seems to have the best of both worlds. Has the lowest possible error, highest possible likelihood, while having the lowest possible complexity. But most likely what people do is they start with the topology and kind of skip around for a while until they find a reasonable topology and they'll stop. But since they are called Bayes networks, they just used to call it, changing the topology of the network. But if it's a neural network, you can actually do the opposite thing. By the way, you can also do it, in this case, I started from sparse topology and added links. I could as well have started with a complete network and started removing links. And seeing, as you keep doing this, the likelihood keeps going down, but the penalty term also becomes smaller. So you'll figure out where is the best place to start. On the neural network side, when the topology is not known, what people do is they'll put like a huge big topology and then start doing what's called optimal brain damage. Okay, because neural networks, you can use all this, brain terminology. So optimal brain damage is I just go into your head and remove a couple of, connections. Okay, and then see what happens. Normally we are not allowed to do it on people, but these are networks, so we can do it. Okay, so that's basically what we do. It's very similar across the two things. And what I'm trying to tell you is it's just very connected set of ideas. One just turns out to be having semantics in terms of the functions, another turns out to have semantics in terms of probability distributions. And then that's the connection with respect to which, where when we talked about why did the deep networks start suddenly becoming more popular, these two slides that I mentioned to you, they were not widely understood at the first coming of neural networks. Because if you remember, in fact, Bayes networks started later than neural networks. So I'm sort of reinventing chronology here. Perceptron started much before. And then independently, the whole Bayes network stuff started. And the first coming of neural networks, these connections were not understood. And when everybody just left the neural network party and went off home and started working on the next fad, people like Jeff Hinton and his colleagues went off to Toronto, where they don't have to get any funding, and they can just keep on working on what they're interested in. And he did this, and for a long enough time, and most of the time making the connections between Bayesian learning and neural networks. Okay, and so in fact, one of the points that I mentioned here, let's see where, is that you can interpret the Markov multilayer neural network itself as a sort of a belief network, which is a Bayes network. Bayes networks are also called belief networks. Okay, and so you use the same topology, but then instead of thinking of weights, you think in terms of conditional probability tables, conditional probability distributions. It turns out what they look at is a particular kind of conditional probability distribution called the sigmoid distributions, which given a node with a bunch of parents, then the probability that that node will be 1 is proportional to its parents' values times some weights from the parents to that node. That's the weight strength of the network. So this for this guy, its probability that will be 1 depends on the current configuration of these nodes and the weights on these networks. Now somehow these weights should become conditional distribution, because for it to be Bayes network, it has to be a conditional distribution. So this is the conditional distribution. It's just a sigmoid network, sigmoid distribution. Okay, and once you do it this way, then you can act as if this network is a Bayes network for a while, and then do some kind of EM, and then set up the current valuation of the weights, and then start doing backpropagation. Now, if some of you are thinking, why these two dual interpretations? Maybe there is one bigger interpretation that is general than both of these. That may well be the case. We just don't know it yet. Yes?
I have a question. So on your previous slide, it said at the bottom that in both cases, Bayes networks and multi-neural networks, we try a few topologies, right? Mm-hmm. So why don't people use genetic algorithms to generate topologies and...
Genetic algorithms?
Yeah.
Please don't ask me to talk about genetic algorithms. I know a lot of people wanted to, but this has no actual connection with this stuff. At some point in time, I can talk about genetic algorithms separately, but they have no connection yet.
I'm just asking in terms of trying to develop topologies without you...
Why would genetic algorithms... Basically, genetic algorithms are a particular optimization technique. Okay, and it turns out for a large number of people basically feel, despite the fact that there is a thriving genetic algorithms community, a large number of people think the metaphor of genetics in a genetic algorithm is unnecessary. It has no actual advantage. Okay, and you made me say it now. So just as there may be cults, and there are a large number of people in that cult, that doesn't necessarily make it a mainstream thing. Okay, so genetic algorithms, there are huge conferences, etc. But you can understand genetic algorithms without thinking of genetics. You can think of it in terms of beam search in hill climbing. Okay, and similarly, somebody wanted me to talk about fuzzy logic. I would say the same thing. Fuzzy logic is the poor man's probability theory. Okay, really poor, dumb, stupid person's probability theory. Okay, and so we won't talk about that either. And saying something works, so we should teach about it, is a iffy issue. Okay, it turns out that you can talk about things that have both semantics and work together. Okay, one other thing, by the way, in terms of topologies, is we talked about this fact that the dropout is an idea that we talked about here in the multilayer neural networks. And the dropout essentially is like the random forest idea, where in essence at different iterations you only update some of the weights. You only update randomly chosen nodes would be, so at any given iteration, a set of nodes are randomly removed. You act as if they don't exist in the network. Because they removed all the connections to those nodes, you don't need to care about them. So you only update the weights for the network, for the nodes that are still available right now. But you didn't actually physically remove them. It's just that in that particular iteration, you only updated some of the nodes, not the other ones. So it's very similar to the idea of random forest, where you didn't remove certain attributes completely from the decision trees. It is just that under one particular decision time, you only took a random set of them. It's as if the others didn't exist for that. But little later, you took a different random set. When some of these will come in, some of those guys will go out. And doing this, again, winds up doing both. It turns out to be a good answer to both the topology and overfitting problems. Okay? Okay, so that's the thing, and we talked about all this stuff last time. I'm not going to redo this again. Further, the multi-layer neural network, of course, even the old days, they're very good at learning certain kinds of concepts where it's actually not easy to write logically. How does one realize that a particular pattern is number 4 or a particular letter is K? If you ask me to write what is the set of rules that I should use to figure out that it is, I have no idea how to write it. Okay, now in those kinds of cases, decision trees will basically wind up crashing, in essence, because they wind up making features which don't have any good significance, and then they'll try to split on those features, and so their typical accuracy is not very good. Multi-layer neural networks, basically, this handwritten digit is kind of strange that because we no longer. You see that as computerization kept going up, we started losing the ability to, we did not have any need to write, and we did not also have any need to talk, right, because we text, right? And now that the computers are actually becoming powerful, they can actually look at your handwriting. They can actually understand what you're saying. It's just that we stop talking now. So maybe that problem doesn't exist. The voice recognition problem doesn't exist because everybody is typing it. But this stuff, of course, it's like a classic problem, and neural networks pretty much are the reigning, top technique. But you also heard of all sorts of other things. General speech recognition in general, multi-layer neural networks have been trained, and those are the ones that seem to be at the latest, highest performance. Same for image recognition. On the huge ImageNet database, multi-layer neural networks are the ones that wind up doing best. Now, again, there is a question of understanding what multi-layer neural networks do in terms of backpropagation, and the question of training a huge multi-layer neural network efficiently. And this is where the two worlds collide. Basically, Jeff Dean was the guy who basically, along with Sanjay Khemawat, invented MapReduce architecture. And that's what, as they say, that Christianity could have existed without Christ, but it couldn't have existed without Paul, St. Paul. Because St. Paul is the guy who kept telling everybody, Christ is a great guy. And Google could have existed without Page and PageRank, but it couldn't have existed without MapReduce architecture. Really, that's its huge big plus point. Okay, and so that guy is, of course, a systems guy, and nowadays he does machine learning. What does he mean by machine learning? He's the guy behind that cat picture thing. So you can recognize cats, and in fact, they also do this recurrent networks where if you show a cat picture at the input, output will say cat. If you put cat in the output, it will start having images that we would tend to think of them as cats. But we are very suggestible, right? So I should show you that actually. There are these beautiful things which show how suggestible we are. If I tell you that there is something, you will see it, But anyway, so the neural networks essentially are like all over the place because of these kinds of the performance. And then I think, as I said, Jeff Dean's contribution is essentially doing this on large scale. Individual pieces are just individual operations that you're doing are essentially these weight setting operations. But you do a huge number of them. Those of you who have any connection to like information retrieval and how search engines work, you know that individual operations are small, you do a large number of them. That's exactly when MapReduce style architectures become very useful. And so that's what is the big thing now. So there are also in the VLSI design, VLSI architectures area, people are interested in coming up with these neuromorphic architectures. Is a neuromorphic architecture essentially a particular architecture that is specialized for training neural networks, multi-layer neural networks fast. You know, those of you who know anything about fast Fourier transforms, when first fast Fourier transforms came, they were just an algorithm. And then, of course, they're just architectures now. Nobody does algorithms. They're essentially already, you know, they're like GPUs. By the way, the connection to GPU is also extremely useful because actually the multi-layer neural networks now, the most of the training is done using the GPUs. Because they don't even need, the normal MapReduce requires Linux kinds of machines. For this kind of computations, you don't even need that. You can just use what the GPUs do. Okay? So suddenly, since something is working, again, as I said, you know, if for a guy with a hammer, everything looks like a nail, right? So it's working, so let's basically push everything that we have into it and then try to apply it to everything. And then at some point of time, it'll break, and then we'll go to the next idea. Okay. This all we did. A couple more things about neural networks. Okay, one thing I want to mention about neural networks, since since you know we're talking about this, is let's compare something like decision trees to neural networks. One of the interesting things is how important, if you say I learned something, how important is it for you to explain what you learned? Do you understand what I'm saying? Okay, neural networks learn, okay? And they learn, and then the way they show that they have learned is by saying, when you say 1, they'll show the number 1. Okay, when they say 15, they'll show the number 15, and you don't ask, how did you figure this out? You are happy enough. But neural networks can also be used to learn which among you are terrorists. And so I have this huge big multi-layer neural network, I'll come and put it on your face. And it says yes. So would you like to know why? You understand? Would you like to know why or not? Typically we would like to know why. Right? And especially many cases when I say here is a hypothesis, I say, what was your reasoning for that? Now you can say, well, my neural network said so. Why? Because the middle layer seems to kind of think, you know, it seems to light up whenever your face is shown. I'm sorry, not you, but. So I kind of feel like, you know, it's a good idea. Now this is a big issue in learning, which is the transparency of the learned knowledge. And there is, you know, here is a, you know, it's been a long time since I told you an anecdote. So here is an old anecdote that, you know, I don't know how apocryphal it is, where there was this one particular time when, in the first coming of neural networks, DoD, Pentagon, of course, is always interested in figuring out how to use the technology. And so they essentially tried to see whether, you know, in a particular set of photographs, if there are hidden armaments like tanks or something. Can you train a network which will just look at the picture? That's exactly what I was doing, right? Look at face and see whether or not they're terrorists, right? And so look at a picture and see if there are tanks hidden. So I show this picture and then should say, there may be tanks hidden here. Okay, and if that is useful, if you can do that, if you can train that, you know, people are happy. I mean, military would be very happy. So they actually, you know, gave somebody some kind of a contract, and these guys essentially applied multi-layer neural network technology, and you know, on some training data, it basically, and they did some training as well as testing, and it got close to 100% accuracy. So obviously, unfortunately, if it was like 60, nobody would have questioned. Okay. It's like, you know, if you have a terrorism detection software, if it says yes, yes, yes to everybody in the room, you will start wondering. Okay, so you should just strategically say 50% of them, or maybe 25% terrorists, the rest, you know, good people. Then nobody will know whether you actually have any basis or not. So this particular thing was saying 100% of the time correctly, you know, this one has hidden tanks, this one doesn't have hidden tanks. And then people were very surprised. Wow, this is amazing technology. How is this happening? It must be a multi-layered neural network with huge number of hidden nodes, etc. And they looked, it actually was a single layer neural network. And it was just basically the only weight that seems to be non-zero was the intensity of the average intensity of light in the picture. That's all it seems to be caring about. So then you start wondering, how is average intensity of light connected to tanks being hidden? You know, are there some kind of black holes that they remove light? Now it turned out that in this particular case, somebody had to actually make training data. They went around and take pictures. Set up, this is how, military contractors get a lot of money. So they set up these scenarios where they took pictures, okay? And obviously they took one day pictures with tanks and another day pictures without tanks, or maybe the same day with tanks first and without tanks afterwards. And the day they took pictures with tanks, it was cloudy. The day they took pictures without tanks, it was sunny. Now, you guys this is a story you can tell in a party and get a lot of laughs. But you're not in a party, you are in 471 Intro to AI. The question is the neural network stupid to have realized that the intensity of the light is the discriminating factor? If in fact all terrorists come in red hats and all non-terrorists come in green hats, there is no namby-pamby about let's not talk about hat-based profiling. That's what you're supposed to do. I'm telling you completely. Right? The question, of course, is the training data is noisy. The training data was not representative. Now, so why is, if you gave the same data to decision tree learner, what would it have said? It would do the exact same thing. This would be one place where decision tree will actually work on image detection. And it too will say average intensity above 3.57 lumens, tank, or below no tank. Now the difference is the decision tree structure is a logical structure. It actually shows the attribute and the question it is asking. So if I say, I'm thinking of a number, ask me 20 questions, and you ask, does that number feel round? Then I'll start wondering, why are you asking these kinds of questions? Right? Basically, we can actually, the moment decision tree learner comes out with the decision tree, you can make sense of it. Neural network, it's just a huge number of, interior nodes. Now, the tricky part is there is like a so this actually, in the beginnings of neural network literature, people were very worried about this problem with neural networks. And so what they will do is they will train the neural network on the data, take the neural network, convert it into a bunch of decision trees. Do you see what I'm saying? Because that sort of makes sense. Now, honestly, what do you think you guys do when you come up with an answer? Like you ask Kasparov, hey, you won the chess match, how did you win? Bozo has any idea at all? No. We all are extremely good at making up an explanation that others can understand. They say, I saw a pattern, and then Lord X came, and then Lord Y came, and then I saw this light, and then I saw that this is the right move to make, and he said, very good. Okay. If on the other hand he said, I went extra 3 layers deep in the search node, you'll say, oh, you must not be really human, you're not very intelligent. By the way, okay, so the point is that we do this. We learn using something like, I don't know whether we have neural networks of this particular type or not, but we learn what we learn and we are good at explaining. And even if our explanations are not right, you would be very unhappy if I were to tell you are a terrorist and I don't give you an explanation. I need to make one up. And then Supreme Court is only going to eventually decide whether or not this is profiling based on the explanation, ultimately. Do you see what I'm saying? So, now the other interesting thing is there are tasks where nobody asks you to explain your decision. If I say, as I say this is 4. Why do you think it is 4? Nobody asks you that. You say this is a good song. I don't ask you why do you think it's a good song. You say this sounds like the word cat. I don't ask you why do you think it sounds like the word cat. In cases, in learning tasks where nobody expects an explanation, neural networks are just as good. Where explanations are needed, you have to figure out what those interior nodes are doing, what those hidden layers are doing. So back on in AAAI 2014, when we were at the, as I said, Intel was giving this talk, just around that time, I don't know if I mentioned this to you guys, Elon Musk was going, having conniption fit, saying, yeah, he's going to take over, you're making this, and half of you are also very worried. I don't know, given the programs you write, you shouldn't be too worried, but, but you're very worried, and that AI is going to take over, and that basically, how do we stop? So we need to ask the program before we deploy it, can you give us guarantees about your performance? And imagine a program which says, don't worry about it, I'll take care of it. That's what a neural network will do. So Elon Musk basically wants a robust and explainable AI. In fact, one of the things that one of the grants that they were actually giving away money at that time for us to say, we'll do work to stop evil AI from taking over the world, and if we do a good enough job, he'll give us money. He has like 10 million and he gave it to a bunch of people. So right around that, we were talking about that in the conference, and we go to this talk by Geoff Hinton, where he says, forget about symbols. Remember that in the whole entire AI, there is this propositional logic which is all about symbols and negations and stuff. And then you come to neural networks where there are no symbols. It's just network with weights. There is this huge, just like frequentist and Bayesian disconnect in statistics, in psychology, there is this whole issue of whether cognition that we do has a symbolic basis or not. Now the interesting thing is, nobody really knows whether cognition has a symbolic basis, but when we talk to each other, when I say I did this, I give you a symbolic explanation. I do a symbolic, the entire communication is symbolic. We don't have brain-to-brain wires. Right? Okay, so, Geoff Hinton was saying, you guys in, symbolic AI people had enough of a good run, forget about it, stop doing that stuff. Because it's all just networks, and if you don't know what the middle parts of the networks are doing, we just ask them, what are you doing? And he seriously actually talked about, connecting the middle layers, the middle units, to a language generation network. And presumably, at some level, you can say that's what probably we do. As I said, we'll do what we do. I'll win a game, or I'll hit you, and then you'll ask why, I'll make up an explanation. My hidden layer basically somehow quickly connects to the language and makes up a symbolic explanation. Is that the real reason I hit you? Is that the real reason I won the game? I don't know. So my idea, which unfortunately did work, was that I will write neural networks, and the safety conscious neural networks, where to check whether the network is safe, I'll ask the middle layer, are you safe? And if it says yes, I believe it. Okay? The question is, how many of you are willing to think that is a way of writing software with guarantees? Do you understand what I'm saying? So there are a lot of you who are worried about how is AI and safety going to go. Well, one technology that works extremely well, you don't understand why it works. In terms of, yes, you understand how it converges in some high dimensional, big error space, but you don't know what those middle things actually mean. Sometimes you don't care what they mean. But the times when you care, big worry. Okay? Okay. So that's about the connection between these neural networks. So what I should do is, in the next 15 minutes, we'll do this, and then we'll take a break, and when we come back, we'll do whatever we can do. Okay. So the two things that I wanted to talk to you about is two ideas which took off when multi-layer neural networks were down in the dumps. And now they're kind of down again because multi-layer neural networks are doing well. And it turns out that they solve the exact same problems with a slight twist. And it's kind of cute to understand what. Okay? So one is, think of this. These are, let's say, positives, these are negatives. It's a classification problem. You're trying to find a line. Perceptron, if you're doing a perceptron, it's a linearly separable case. If you give a perceptron, this data, it will find a line. Which line will it find? It will find the line that has zero training error. That means any line that I can draw between this, I will call it cluster or convex hull, and this cluster, any line I can draw between them, which separates one from the other, is equally good in terms of error. They all have zero error. Exactly zero error. In fact, this is why I said, in doing perceptrons, I said the hypothesis complexity we don't care. It's because the error is zero and hypothesis, as I said, the topology is the same, so hypothesis complexity doesn't matter. But it turns out, actually, you can argue that if I were to say this is a line or this is a line, each of them perceptron would give. You won't know which one it would come to. It will come to them and then say both of them will have zero error, so there is no reason for it to go any further. Agreed? Because in the weights, in the error surface, both of them are at zero. Both lines correspond to zero error. Okay, so the question is, do you guys care between this dark blue and this dotted blue? Do you guys care which line is better?
Solid blue.
Solid blue. Everybody is into solid blue, right? Why?
Solid.
Well, you're like your neural networks. Make up something quickly. You felt, hey, like looks good, nice and solid. But why? That's exactly. By the way, this is about the previous one too. People make quick judgments, and then when you press them, they'll quickly use their language facility to make nice big sentences. It's not that people don't stereotype; they just cover their tracks very well. Okay, so anyway, so the reason you guys are liking this, as some of you seem to be saying, is it is going to be less sensitive to the placement of the dots. This guy would wind up having non-zero error if in fact this comes slightly this side, that's it. Or this comes slightly this side. This is giving itself the maximum amount of margin between the two convex hulls. By the way, the word convex hull is, if I give you a point, you sort of think of like a loose convex shape, that is around those points. That's the convex hull. Okay, so it turns out that you are looking for max margin lines. Not any line, but a max margin line. The line that is maximally far away from the two clusters. Now the question is, how do you figure out what does it mean? Given that it's the two clusters, how do you figure out what the margin is? You need to consider for any given line, once you put a line, any given line, you can talk about what are the closest points from each of these convex hulls to this line. Points are also called vectors. In some sense, those 2 points are holding up this line. They are support points. So they are called support vectors. You see where I am going with this? So you're finding the 2 points for any given line, you're finding the negative point